Okay, in this question we're looking for the car's position at two different times. In this problem we're given information which this starts at t equals 0 seconds and this goes to t is equal to 6 seconds. We know that the distance between these 2 points is going to be 144 meters, so we can say x initial is equal to 0 and x final is equal to 144. The first question is asking us what is the car's position basically at this halfway point on the timeline. Because it's accelerated motion, it's actually going to be more like this, somewhere to the left of the midpoint. And then we also want to know where is it going to be if we project this into the future to t is equal to 9 seconds, where is the car going to be? So we'll say this is x9. Alright, so that's what we're looking for. Next thing we need to do is to set up our lists of information. So initially we're going to have information for x6. So we know that x initial is equal to 0. X final, they tell us, is 144 meters. V initial is equal to 0. V final is an unknown quantity. The acceleration is also an unknown quantity. And of course the time there was 6 seconds. Now, we're looking for, first, in part A, what is the position x3? So the information here that we need is that the car is starting out at x equals 0 once again. The final position is what we're looking for. The initial velocity is 0. The acceleration is an unknown quantity. And time is equal to 3 seconds. When solving problems, I like to keep everything in closed form, that is, all letters, from start to finish until the very end. The very last thing you should do when problem solving is putting the values for your variables into your equation. If you do it beforehand, then you're not using good solution form, and it's really good practice to do that because these are the types of skills that you need to be successful on the AP exam. Because many of the questions you're given on the AP exam are not going to have number values with them. Some questions are what we call semi-quantitative or proportional, and many of them don't even do that. So you need to be able to work with letters only and understand how to interpret what that means. So whenever I go through solutions, the only time I ever substitute numbers in before I get to the very end of the problem is going to be whenever the algebra becomes particularly ridiculous. And you'll see times like that as we go throughout the year. The other time that we won't do that is whenever we have a quadratic, because it's rather difficult to get algebraic substitutions using the quadratic formula. So when you reach that barrier, it's time to move on and start using numbers. The first thing we're going to do is we're going to model the motion for the car during the first 6 seconds. This may be important later on, I don't know, but we're going to model it anyways. So what we have to do is select an equation which we think best models the motion. So we could use the position function. V initial is 0, so we just get d is equal to 1/2 at squared. That could be very useful because we know the displacement, we know the time, and the acceleration is not given anywhere in the problem. So if we solve this equation for acceleration, then we have an expression that we can use to eliminate the acceleration variable later on. The acceleration independent equation probably wouldn't work so well because it doesn't have acceleration in it. And the the velocity or the time independent equation, again, that's not a really good one because we don't know v final. You could look at your definitions, and when we look at our definitions, the only equation that would make any sense is the equation for average acceleration, but again, we don't know v final. So it would appear, at least on the surface, that the best equation to use is the position function. So for the object at 6 seconds, we're going to get d6 is equal to v initial t plus 1/2 at squared. V initial was 0, and so we get x final minus x initial is equal to 1/2 at squared. And this is for 6 seconds. This is x final for 6 seconds. Knowing that the initial position is 0, I'm going to make that go away, and I get a final expression that says x final 6 is equal to 1/2 a t6 squared. Solving for a, because I'm expecting I may have to do that later, a is going to be equal to 2x final 6 divided by t6 squared. Alright, so this is probably going to be pivotal in our problem. Now let's take a look at x3. And we want to know what was the car's position at 3 seconds. Well, if we go back to our equations, you're going to see that because v final is an unknown quantity, I forgot to list it here, v final is unknown, but because v final is an unknown quantity, the only equation that's going to be efficient for us is going to be to use the position function. So we're going to get d3 is equal to v initial t plus 1/2 at squared. We know that v initial was 0, so we get x final minus x initial is equal to 1/2 a t3 squared. Now x initial, again, was 0 right there, so we're going to make that go away. And we get x final 3 is equal to 1/2 a times t3 squared. So this is what we're looking for, x final 3. We wanted to know what was the position. Now the acceleration is not known, so we get that by using this equation we derived earlier. So we'll substitute everything on that right side. So we get x final 3 is equal to 1/2 times the quantity of 2 x final 6 divided by t6 squared. And now we have t3 squared. So this 1/2 cancels with that 2. And if we go through our checklist of information of what we know and don't know, x final 6 is known, that's 144. t3 is 3 seconds, and t6 is 6 seconds. So now we have a solvable problem. So x final 3 is going to be equal to x6 was 144 meters divided by t6, so that's 6 squared, that's going to be 36, times t3 squared, which is 3 squared, or 9. So let's get out our calculator. We're going to have 144 divided by 36 times 9, and that's going to give us a position of 36 meters. Okay, so now we need to figure out what's going on at x equals 9 seconds. And at x equals 9, a lot of this information is the same. We know x initial is equal to 0. X final is what we're looking for. V initial is equal to 0. V final is an unknown quantity. The acceleration is going to be the same throughout, which is still technically an unknown quantity. And then we have time, which is 9 seconds. Okay, so I'm going to start this one a little differently just because I want to demonstrate the method more purely, which is to say that if you want to know what's happening at x equals 9, then we start by finding an equation for the object that represents its motion the best. So looking at our equations, because we don't have v final anywhere, the best one to use is going to be the position function. So we'll write that. So we get d9 is equal to v initial t plus 1/2 at squared. V initial is 0, so we get x final 9 minus x initial 9 is equal to 1/2 at9 squared. X initial was 0, so we get x final 9 is equal to 1/2 at9 squared. Now this is the part that's going to look a little different. I started off by saying that why don't we solve this, write an equation for x6, and then we'll solve it for acceleration, anticipating we're going to need it later. Well, that's a little bit backwards from the way we normally do it, because you don't always have that kind of foresight. So what would you do if you didn't think to do that? Well, first you go through your checklist, and x final 9, that's what we're looking for, so that's not a problem. Acceleration is unknown, but t is known. So what would I do? I would draw an arrow coming from A, and I'd work off to the side. And I would ask myself, what equations, might be helpful in determining what that acceleration value is? So generically, any equation with acceleration in it becomes a valid option. What you cannot do is use the position function for a second time using the information for x9. So the time-independent equation is not going to be very helpful, nor would the acceleration independent equation be very helpful, at least on the surface, because we don't know what v final is. So that's going to force us to have to make things more complicated to finally get to our answer, because we're going to have to find a substitution to get rid of v final. And how would you do that? That would be by using the average acceleration equation. So it would appear that it's probably best to start using the information for the first part of the motion, x6. And because we're using data for x6, that's like a completely different part of the problem. So any one of these equations become valid equations once again. And as we did earlier, it would appear that the position function is probably going to be the most efficient way of coming up with acceleration. So first, let's do this, what would be the obvious choice. You look at this and you say, okay, I need acceleration. Oh, here it is. I have acceleration. So we're going to write A is equal to V final minus V initial over T. And V final, you're like, well, I don't know what that is. So that's an unknown quantity. V initial, that's going to be 0. And time, I know that that's going to be 9 seconds. So this is going to become T9. Now, what do I do about V final? Well, V final, you're going to have to go to another equation. What equation has V final in it that might be helpful? Well, it could be D is equal to 1/2 V initial plus V final times T. So let's try that. We certainly wouldn't want to use the time-independent equation because that's going to put acceleration back into our equation. So we get 1/2 V initial plus V final times T. And so V initial is going to go to 0. And so V final is going to be equal to 2D divided by T. So what that means is acceleration is equal to 2D over T divided by T9. So what D are we referencing here? Well, this D should be D9 and this t should be t9. So if we simplify that, we get 2d9 over t is going to be t squared, t9 squared. Now we'll substitute that back into our equation and see what happens. So we get x final 9 is equal to 1/2 times the quantity of 2d9 over t9 squared times t9 squared. And so t9 squareds cancel each other out, and we get x final 9 is equal to 1/2. Oh, 1/2 and the 2 cancel out. So we get x final 9 is equal to x final 9 minus x initial. X initial is 0. And we end up with this nonsense statement right here that says x final 9 equals x final 9. So that means basically we're going to have to go to what was happening at in the beginning with x6. We cannot rely entirely on just the information from x9. There's just not enough information here, and so we're going to have to include other information. So we go to this other part of the problem, and this other part of the problem we've already done the work for. So knowing that all of this stuff here did not work out, none of this worked out, that means we're going to have to go on with the other part. Okay. So let's start over. So we get x final 9 is equal to 1/2 a t9 squared. Now, acceleration, it's still the same process. So when it comes to the acceleration, we get a is equal to 2x final 6 divided by t6 squared. So x final 9 is equal to 1/2 times 2x final 6 divided by t6 squared times t9 squared. Cancel out the 1/2 with the 2, and now we're almost done. X final 9 is equal to 144 divided by 6 squared is 36 times 9 squared, which is 81. Let's pull up our calculator, and we get 144 divided by 36 times 81, and our new position is 324 meters.